Before part 2 continues, let us bring part 1 back onto the table. Hashy learned that a hash table is a set of rules that must agree. A key turns into a number. The table size turns that number into a home slot. If two keys ask for the same home, there is a collision. In part 1, Hashy handled that by walking forward with linear probing. Search had to replay the same walk. Deletion needed tombstones because simply erasing a cell could break future searches. And when the table became too crowded, resizing meant placing records again under a new table size. So part 2 starts with a table that works. The records are findable. Now the question is sharper. When collisions are unavoidable, which strategy should shape the table? That question starts before the collision strategy runs, because every strategy inherits the first slot choice. Hashy first checks a common assumption. If the keys are unique, is the table already safe? Not necessarily. Unique keys only mean the records are different from each other. They do not guarantee different home slots. The keys 1000, 2000, 3000 and 4000 are all different records. But with key modulo 10, everyone ends in 0. So everyone lands in slot 0. Identity is solved, but distribution is not. The hash function decides how often crowded home slots are created. The collision strategy decides what happens after that crowding begins. To improve the first choice, Hashy needs more of the key to influence the home slot. Folding is a simple way to see that idea. It is not the only way to build a hash function, and modern systems often use stronger mixing. But folding is useful because the logic is visible. Instead of letting one small part of the key dominate, Hashy breaks the key into chunks and combines them. In shift folding, the chunks keep their direction. 1, 2, 3, 4, 5, 6 and 7, 8, 9 are added as they are, giving 1, 3, 6, 8 before the table size maps it to a slot. Boundary folding changes one detail. Alternate chunks are reversed first, so 4, 5, 6 becomes 6, 5, 4. Now different digit positions line up during the addition and the result becomes 1, 5, 6, 6. The point is not randomness. The point is to let more parts of a structured key affect the final home slot. With that in mind, Hashy can return to the home slot more carefully. Now the home slot is not just the first box in the row. It is the starting point for everything the table does next. The key is transformed. The table size maps that value into the available range. Then the record gets the place it wants to try first. If those first choices are uneven, the collision rule starts under pressure. Some slots collect too many records. Some searchers have to walk farther. Some cleanup becomes harder. So hash quality and collision handling belong in the same story. Mapping decides where pressure appears. The collision rule decides how the table responds. A better home slot spreads the pressure out, but it does not remove collisions. The table is finite, and records keep arriving. So now Hashy can move from mapping to the collision decision itself. Imagine the mapping is better now. The table is no longer obviously broken. The keys spread out more evenly. Still, sooner or later, two records ask for the same home slot. This is where part 2 really begins. The table has already answered where the record wanted to go. Now it must answer where the displaced record actually goes. That answer changes the shape of the structure. Maybe the record attaches outside the slot. Maybe it stays inside the array and walks forward. Maybe it jumps by a formula. Maybe another hash gives it a different rhythm. A lookup later must follow the same rule that insertion used, or it may stop too early. So Hashy is not choosing a tiny detail. Hashy is choosing the movement rule of the table. The first option is to stop forcing every collision into the main row. That option is chaining. In chaining, a slot can become a bucket. The main table still gives Hashy a home slot, but the slot can hold a small collection of records behind it. If 3 records choose slot 4, Hashy does not push the second and third records into other cells of the main row. They attach to slot 4 as a chain. Search is direct, go to the home slot, then compare keys inside that bucket until the record is found or the bucket ends. Deletion is also simpler than linear probing because removing one bucket item does not break a probe path through the main table. Chaining can even handle a load factor above 1 because there can be more records than main slots. The cost is extra structure. Buckets need memory, and lookup may jump away from nearby cells. Chaining gives Hashy a comfortable collision story, but it gives up some locality. That is why open addressing is still worth considering. So Hashy asks the natural follow-up. The chaining is so comfortable. Why not always use it? Because open addressing keeps every record inside the table itself. The array is the storage area that can be compact and it can be friendly to nearby memory access. Instead of jumping from a slot to a side structure, search can inspect cells in the same row. But open addressing makes the path through the table part of correctness. Empty cells, occupied cells, and deleted cells all mean something. Insert and search must follow the same route, or a record can become unreachable even though it is still in the table. So this is the trade. Chaining buys flexibility by leaving the row. Open addressing buys compactness by staying inside it. Once Hashy stays inside the row, the walking pattern becomes the next problem. The walking pattern Hashy already knows is linear probing. If the home slot is full, try the next slot. If that is full, try the next one and keep moving one cell at a time. This is simple and it can be fast because nearby cells are checked together. But the same straight walk creates primary clustering. Once a run of occupied cells forms, it becomes a crowded neighborhood. A key that lands inside the run has to walk through it. A key that lands just before the run also has to walk through it. When that key finally finds an empty slot, it often extends the run. So the cluster attracts more probes, and those probes make the cluster longer. The table can still be correct, but correct is not the same as fast. Hashy now needs a way to stop every collision from marching down the same straight road. Quadratic probing changes that road. Instead of moving by one cell, then two cells, then three cells, Hashy uses squared offsets. Try home plus 1 squared, then home plus 2 squared, then home plus 3 squared, wrapping around the table. Visually, the probe stops marching through one neighborhood and starts making wider jumps. That helps with primary clustering, because a single adjacent run is less likely to absorb every nearby collision. But this is not magic. If two keys have the same home slot, they still try the same retry path. For example, both would try home, then home plus 1 squared, then home plus 2 squared, then home plus 3 squared. That shared retry path is the secondary clustering caveat. So quadratic probing improves the shape of the walk, but it does not give every key its own route. That leads Hashy to double hashing. Double hashing gives Hashy one more source of movement. The first hash still chooses the home slot. A second hash chooses the step size for that key. Now two keys can collide at the same home slot and still explore the table differently. One key might move by 3 cells each time. Another might move by 5. This reduces the chance that many probe paths pile on top of each other. It can spread work more evenly than linear probing, and it avoids some of the shared path behavior of quadratic probing, but it needs care. The second hash must produce useful step sizes. The step size must also work with the table size, or a lookup can cycle through only part of the table and miss empty space. So double hashing is powerful but not free. With all 4 choices visible, Hashy can finally compare the trade-offs. So which strategy should Hashy choose? There is no universal winner, so the useful move is to compare the workload against the cost. Take 2 rows. If the table expects lots of deletion, uneven load, or more records than main slots, chaining starts to look attractive. It keeps deletion simple and handles high load more comfortably, but it gives up some locality and needs extra structure. If the table needs compact storage and fast scans through nearby memory, linear probing starts to look attractive. It can be very quick when the load is controlled, but deletion is delicate and primary clusters can make walks longer. The same style of analysis applies to quadratic probing and double hashing. Ask what the workload needs, then ask what the strategy gives up. And behind all of them is the maintenance rule from part 1. When load factor gets too high, resizing usually means recomputing home slots with the new table size and placing records again. That is the main takeaway. A hash table stays fast because mapping, collision handling, deletion, load factor, and resizing are designed together. If this made hash tables clearer, subscribe for the next one.